By the early 1990s, American railroads finally had the horsepower they had always wanted. After decades of incremental improvements, General Electric delivered a locomotive that could move freight faster and more efficiently than anything that came before. The C40-8W represented the culmination of everything the industry had been asking for. What they didn't have was the fueling system to support it. The GE C40-8W didn't run out of fuel because it was inefficient. In fact, for its output, it was remarkably economical. It ran out of fuel because the entire railroad infrastructure surrounding it, the fuel racks, the delivery schedules, the yard procedures, had been designed for a different era, an era of smaller engines, shorter trains, and lower sustained power demands. This is the story of what happens when technology advances faster than the systems built to support it. The C40-8W didn't fail. It simply revealed that American railroading had entered a new scale of operations, one where fuel delivery mattered every bit as much as horsepower. For most of the post-war period, American freight locomotives settled into a comfortable equilibrium around 3,000 horsepower. The EMD SD-42, introduced in 1972, became the defining locomotive of its generation. At 3,000 horsepower, it struck a balance between pulling power and operational practicality. Railroads built their entire infrastructure, their fueling systems, their maintenance schedules, their yard layouts, around what a 3,000 horsepower locomotive required. Through the 1970s and into the early 1980s, this equilibrium held. Yes, there were more powerful units available. EMD offered the SD-45 at 3,600 horsepower, but the industry largely stuck with what worked. The SD-42 sold over 3,000 units precisely because it fit so neatly into existing operations. Then the competitive pressure intensified. By the mid-1980s, deregulation under the Staggers Rail Act of 1980 had fundamentally changed railroad economics. Carriers could no longer survive on captive traffic and regulated rates. They needed to move more freight, faster, with fewer assets. The pressure to reduce operating ratios, the percentage of revenue consumed by operating expenses, became relentless. General Electric, long the second-place builder behind EMD, saw an opportunity. Their -8 series, introduced in 1984, brought microprocessor controls to locomotive technology. But the real breakthrough came with the C40-8 and then the C40-8W, which added the distinctive wide-nose safety cab that would become standard across the industry. At 4,000 horsepower, these locomotives represented a genuine leap. This wasn't a modest upgrade. This was a 33% increase in output over the SD-42 that railroads had been running for 15 years. The implications seem straightforward. With 4,000 horsepower units, you could run fewer locomotives per train. A train that previously required 6 SD-42s might now run with 4 or 5 C40-8Ws. Fewer units meant lower maintenance costs, fewer crew complications, and better fuel efficiency per ton-mile moved. On paper, everything pointed toward dramatic savings. What nobody fully accounted for was what those 4 or 5 high-output units would demand from the support infrastructure. The critical assumption, never really examined closely, was that railroads could slot these new locomotives into their existing fuel ecosystem without major changes. After all, a locomotive is a locomotive. It pulls up to the fuel rack, takes on diesel, and departs. How different could it really be? The answer would prove uncomfortable. Before we continue, if you think our content is unique and informative, please leave a like and subscribe. It really helps support the channel. Also, make sure to share the video with other train fanatics out there. The GE 7FDL-16 prime mover inside the C40-8W was a sophisticated piece of engineering. 16 cylinders, each displacing 668 cubic inches, producing 4,000 horsepower at 1,050 RPM. For its output, it burned fuel efficiently. The specific fuel consumption, pounds of fuel per horsepower hour, was competitive with anything on the market. But efficiency per unit of output is not the same as total consumption. And here the math became challenging. A locomotive throttle has 8 notch positions plus idle. At idle, a C40-8W sipped fuel at modest rates, perhaps 3 to 4 gallons per hour. At notch 8, full power, consumption could exceed 200 gallons per hour. And unlike switching operations, where locomotives spend most of their time at lower throttle positions, mainline freight demanded sustained high output running. The trains themselves were changing. Through the late 1980s and into the 1990s, train lengths grew steadily. A train that might have run at 80 cars in 1975 now commonly stretched to 100, 110, even 120 cars. Tonnage per train increased accordingly, and all that additional weight required sustained pulling power across long distances. Consider a loaded coal train climbing toward a mountain grade. The locomotives might run at notch 7 or notch 8 for hours at a stretch. At 180 to 200 gallons per hour per locomotive, a 5-unit consist could burn through 4,000 to 5,000 gallons before reaching the summit. That's a substantial portion of the fuel tank capacity consumed in a single extended pull. The C40-8W carried approximately 4,000 gallons of diesel in its standard tank configuration. That sounds like a lot until you calculate the consumption rate during sustained high-output operations. A locomotive running at notch 8 could theoretically empty its tank in roughly 20 hours of continuous operation. Factor in the reality of road service, the grade crossings, the meets with opposing traffic, the speed restrictions, the helper districts, and fuel margins became uncomfortably thin. But here's where the compounding effect entered the picture. One locomotive with a 4,000-gallon tank wasn't necessarily a problem, but railroads don't run single units. They run consists of 3, 4, 5, sometimes 6 high-horsepower units on a single train. When a consist arrived at a fuel rack, it didn't need 4,000 gallons. It needed 15,000 or 20,000 gallons, and it needed that fuel delivered in a time frame that kept the railroad running. This is where we need to shift our thinking from fuel consumption rate to fuel throughput. The C40-8W's consumption rate, gallons per hour, was higher in absolute terms than older units because it produced more power. That wasn't a flaw, that was physics. The problem emerged when you tried to push that much fuel back into the tanks in a reasonable amount of time. The fueling infrastructure hadn't been designed for this scale of throughput. It had been designed for an earlier era, when locomotives were smaller, trains were shorter, and the pace of operations was different. That mismatch would prove consequential. The typical fuel rack at a railroad terminal in the late 1980s hadn't changed dramatically in decades. A fuel rack is, fundamentally, a pump station. Diesel fuel comes in from storage tanks, passes through filtration, and gets pumped into locomotive tanks through delivery hoses. The system works. It had worked for years. The constraint was flow rate. Most fuel racks of that era delivered diesel at rates between 100 and 200 gallons per minute through a single hose. At 150 gallons per minute, filling a 4,000-gallon tank took approximately 27 minutes, assuming the tank was completely empty, which it rarely was. Add the time to position the locomotive, connect the hose, verify the fuel quantity, disconnect, and move to the next unit, and you were looking at 35 to 40 minutes per locomotive as a practical minimum. Now, multiply that by a 5-unit consist. You're talking about 3 hours of fueling time just to service one train. And most terminals didn't have multiple fuel racks operating in parallel. They had one rack, sometimes two, serving all traffic through that point. The delivery side of the equation created additional constraints. Diesel fuel reached most railroad terminals by tank car. Tank cars arrived on scheduled movements, held limited quantities, and required time to unload into terminal storage. The entire supply chain operated on assumptions about consumption rates, assumptions calibrated to the 3,000 horsepower era. Remote terminals felt the pressure most acutely. A yard in an urban area might have road access for truck delivery as a backup, but a helper base at the foot of a mountain grade or a crew change point in an isolated location depended entirely on rail-delivered fuel. If consumption outpaced delivery, there was no quick fix. Many railroads had moved toward just-in-time fuel management through the 1980s. It made financial sense. Holding large fuel inventories tied up capital. Better to coordinate deliveries closely with consumption, but just in time. Systems have no margin for error. When consumption suddenly increased by 30% or more, as it did when high-horsepower units became prevalent, the buffers disappeared. The operational reality became visible in yards across the country. Trains arrived with fuel gauges showing empty or nearly so. Locomotives queued at fuel racks, waiting their turn. The queue backed up, blocking tracks needed for other movements. Crews reached their hours of service limits while their trains sat waiting for fuel. Dispatchers juggled meets and passes around trains that couldn't move because they hadn't been serviced. And here was the frustrating part. The fuel existed. Storage tanks held diesel. Tank cars sat in yards waiting to unload. The commodity itself wasn't scarce. What was scarce was the rate at which it could be transferred from storage to locomotive. A railroad could have 1 million gallons of diesel in terminal storage and still have trains delayed for fueling if the pumps couldn't deliver it fast enough. The bottleneck wasn't supply. The bottleneck was throughput. This distinction matters because it shapes how you think about the problem. If the issue were fuel scarcity, you'd solve it by buying more diesel. But the issue was infrastructure capacity. Solving it required capital investment in physical plant, new pumps, new racks, new delivery systems. That took time and money that railroads under severe competitive pressure were reluctant to commit until the scope of the problem became undeniable. For several years in the early 1990s, the mismatch persisted. High horsepower locomotives operated within fueling systems designed for their predecessors, and the friction showed up in delays, missed connections, and frustrated operating personnel at every level. The fueling problem didn't exist in isolation. It cascaded through every aspect of terminal operations. When a train arrived at a terminal for crew change and servicing, it entered a carefully choreographed sequence: inspect the cars, test the brakes, service the locomotives, fuel, sand, oil, coolant, brief the new crew, release the train for departure. Each step had an expected duration. The whole sequence was supposed to flow. When fueling time doubled or tripled, the sequence broke down. Dwell time, the total time a train spends stopped at a terminal, became unpredictable. A train that should have been through servicing in 2 hours now sat for 4 or 5. Crew scheduling, built around expected arrival and departure times, fell apart. Fresh crews showed up and waited. Crews already on duty approached their 12-hour hours of service limits, with their trains still in the yard. An hours of service violation wasn't just an inconvenience. Federal regulations prohibited crews from operating beyond their limits. If a train couldn't depart before its crew timed out, you needed a new crew. If no new crew was available, the train sat. Other trains stacked up behind it. The yard congested. The congestion spread. The C40-8W fleets felt this pressure disproportionately for several reasons. First, their larger fuel tanks, while providing more range, also required more time to fill. A 4,000-gallon tank takes longer to fill than a 3-to-1 500-gallon tank at the same pump rate. Simple physics. Second, the railroads deployed their newest, most capable power on their highest priority trains. The C40-8W fleets concentrated on the premium intermodal routes and the heavy unit train districts, exactly the services where delays hurt most. Third, the wide cab configuration that gave the C40-8W its W designation affected servicing in subtle ways. The wider cab meant longer units. Longer units meant more repositioning at service areas designed for older equipment. Small inefficiencies accumulated. At the dispatcher level, the frustration was acute. A dispatcher's job is to keep trains moving through a territory efficiently. When trains sit in terminals for extended servicing, the dispatcher loses control of the railroad. Meets that were planned hours in advance become invalid. Passing sidings fill up. The fluidity that makes a railroad efficient evaporates. The dispatcher might have a priority train ready to go, crew on board, cars inspected, everything in order, and that train couldn't leave because 2 of its 5 locomotives were still at the fuel rack. The mathematics of fuel delivery determined when the train could move, regardless of any other consideration. This created a kind of operational helplessness. Traditionally, dispatchers could solve problems through routing decisions, through strategic use of sidings, through adjustments to train speeds. But you can't dispatch your way out of a fuel rack bottleneck. The train moves when the fuel is aboard, and not before. Night operations compounded everything. Many railroad terminals reduced staffing during overnight hours. Fewer personnel meant slower servicing, but traffic didn't stop at night. Trains that arrived during the small hours might wait until morning for full service, adding hours to their transit times. The situation was sustainable in the sense that trains eventually got fueled and moved, but it was corrosive to operating efficiency. Railroads measure performance through metrics like average velocity, terminal dwell, and on-time performance. All of these suffered when fueling couldn't keep pace with consumption. Initially, railroads tried procedural fixes. They adjusted fueling thresholds, triggering refueling at higher remaining quantities to provide more margin. They integrated fuel planning more closely with train dispatching, trying to anticipate needs before trains ran dry. They experimented with consist-level fuel tracking, monitoring the aggregate fuel state of all locomotives on a train rather than just individual units. These measures helped at the margins, but couldn't solve the fundamental throughput problem. The pumps delivered what the pumps delivered. No amount of planning could make fuel flow faster through infrastructure designed for another era. Through the mid-1990s, major railroads began systematic upgrades to their fueling infrastructure. Higher capacity pumps replaced older equipment. Flow rates increased from 150 gallons per minute to 300 or more at major terminals. Multiple fueling points allowed several locomotives to fuel simultaneously. What once required one rack now might have 3 or 4 positions in parallel. Storage capacity increased as well. Larger terminal tanks provided buffer against delivery delays. Multiple delivery options, tank cars plus highway tankers, where practical reduced dependence on any single supply chain. The evolution of tank car operations mattered too. Faster unloading systems accelerated the transfer of fuel from rail delivery to terminal storage. The whole supply chain, from refinery to locomotive tank, came under scrutiny. These changes didn't happen overnight. Infrastructure investment on railroads moved slowly by necessity. Environmental permits for fuel storage facilities require time. Construction at active terminals must work around ongoing operations. Capital budgets compete with other priorities. But by the late 1990s, the major carriers had largely resolved the fueling bottleneck. When GE introduced the -9 series, the successors to the -8 line, railroads were better prepared. They had learned that new locomotives required investment not just in the motive power itself, but in all the supporting systems. The lessons applied beyond fueling. Higher horsepower units demanded more from maintenance facilities, from parts supply chains, from crew training programs. The entire logistics ecosystem around locomotive operations needed to scale with the power plant. Procedural changes became permanent. Fuel management evolved from an afterthought to a core competency. Sophisticated software tracked fuel consumption across fleets, predicted needs, and optimized servicing locations. What had been manual and reactive became automated and predictive. When AC traction locomotives arrived in the mid-1990s, the SD70 from EMD, the AC4400CW, and AC6000CW from GE, the industry was ready. These units pushed horsepower even higher, but the infrastructure had finally caught up. Looking back, the C40-8W wasn't the villain of this story. It was the catalyst. Every technological advance creates friction with existing systems. The automobile challenged roads built for horses. Jet aircraft overwhelmed terminals designed for propeller planes. Container shipping transformed ports that had handled break bulk cargo for centuries. In each case, the new technology forced infrastructure to evolve. The C40-8W did the same thing for American railroad fueling systems. It exposed a gap that had always existed, but never quite mattered before. Previous generations of locomotives had sufficient power margins to work within undersized fueling infrastructure. The C40-8W didn't have that luxury. Its capabilities demanded supporting systems that matched its output. The broader lesson extends beyond railroads. Scale changes rules. A system that functions adequately at one level of throughput may fail completely at a higher level. The failure isn't in the individual component, the locomotive, in this case, but in the mismatch between component capability and system capacity. What followed the C40-8W generation reflects this learning. The -9 series, introduced in 1993, built on the -8 platform with refinements informed by operational experience. Railroads ordering -9 units simultaneously invested in the infrastructure to support them. The planning became holistic. AC traction, which began to transform railroad motive power in the mid-1990s, brought even greater capabilities and even greater demands. The lessons learned from the C40-8W fueling experience shaped how railroads approach these. Next-generation units. Network-level fuel management, once an afterthought, became standard practice. Today, the descendants of the C40-8W, the Evolution series from GE, now Wabtec, operate within sophisticated support ecosystems. Fuel is tracked in real time. Consumption is predicted algorithmically. Infrastructure is scaled to anticipated demand. The problems of the early 1990s seem almost quaint, but the C40-8W era deserves remembrance because it illustrates how technology and infrastructure must evolve together. A locomotive is not just an engine, it's a node in a network. Its performance depends not just on its design, but on everything around it. The GE C40-8W didn't burn fuel too fast. It revealed that American railroading had entered a scale where fuel delivery mattered as much as horsepower. That revelation, uncomfortable as it was at the time, ultimately made the industry stronger, more efficient, and better prepared for the high-output future it was entering.